Okay, in the third problem, we've got a shot putter, puts the shot up in the air, straight up. Says, watch this. Throws it up, hopefully steps aside before it comes down, and the shot gets damaged and hitting his head. Guy's got to have a pretty thick head, don't you think, to do that? So probably wouldn't get hurt, but the shot might get damaged. You don't want a dented shot. Okay, well, now it's very helpful to list the quantities that we use in analyzing motion. Now these are the quantities that we use to model motion. Those are the quantities that appear in the equations, but of course we've also got delta V and delta T. And it's a good idea to just note all these and then note which ones you're given. In this case, we're given that the shot is released from 2.2 meters high. 2.03 meters high. And the guy's head is at 1.7 meters. Okay? From that, we can determine delta S very easily. The shot starts out at 2.03 meters and ends up at 1.7 meters, so it has a net displacement of negative 0.33 meters. Now, understandably, people were inclined to want to say, well, let's analyze this in two phases. We can easily figure out the motion going up, and then we know how high it is. We can figure out how far it has to fall and how long it's going to take for each of those phases. That would be okay. I would find that acceptable. This is something you need to be aware of, so this is the way I've chosen to analyze the problem. So we know the initial velocity, upward at 9.2 meters per second. And we're going to assume that upward is positive, okay? So we can choose either, positive here or positive here. But once we've made the choice, we're stuck with it throughout the rest of the problem, okay? Otherwise, we're going to get very confused. So we choose upward to be positive. And as I said in class, you really want to write that assumption down for yourself as well as for whoever's going to be reading or grading your paper. Okay, then, since upward is positive, the acceleration is negative 9.8 meters per second squared, the acceleration of gravity. Now we've got a delta S, a V naught, and an A. What more do we need? We need nothing more. In this situation, now somebody said, well, we can use the third equation of motion to find delta T, because that's really what we're after. We can, but the third equation is quadratic in delta T, and that can be difficult to interpret. It's easier to interpret your result for final velocity if you use the fourth equation, and you can use the fourth equation with these quantities just as easily as you can the third. Now you're not going to get delta T directly, you're going to get a final velocity, but then we would know final velocity, initial velocity, and delta S. We can easily find delta T. Okay, well, what's the final velocity? It's easily found from the fourth equation because we know V naught A and delta S. Take the square root. Well, if VF squared equals this, then VF is plus or minus the square root of this quantity. And we calculate this, and we get our final velocity. Then, as I've said, we would know the initial and final velocity, so we could find the average velocity. And then average velocity being delta S over delta T, we get delta T equals delta S over average velocity, and we easily get the solution. That's the scheme. Okay, and it's good to have that scheme, good to understand that scheme, good to be able to see those schemes before you start putting numbers into a problem. Okay, well, having outlined the scheme, let's see what we have. Okay, since we know these three quantities, of course, we find VF. Now, V naught is 9.2 meters per second. When you square that, you get about 85 or 86 meters squared per second squared, I think, just doing that kind of intuitively. And then delta S is negative 0.33 meters. A is negative 9.8 meters per second squared. You multiply those, you get something pretty close to about 3 meters squared per second squared. Add that to 2 and multiply that by 2, and you get about 6 meters squared per second squared. So that's going to be about 91 centimeters squared per second squared. And when we take the square root, it's going to turn out to be somewhere between 0.2 and 0.3 meters per second higher than your initial velocity. But then, of course, we have the plus or minus. So I'm going to say we're going to get something about 9.5 meters squared per second, 9.5 plus or minus 9.5 meters per second. Now, which do we choose, the plus or the minus? Well, this is our final velocity. What direction is the shot going to be coming when it reaches the 1.7 meter position of the shot putter's hopefully absent head? Not that he's absent his head, that his head will be absent from that position. Well, obviously, the shot's going to be coming down, and upward was positive. So PF is going to be negative 9.5 meters per second. Now, this is very approximate. This is not going to give us a really good result. You would want to use your calculator to get a much more accurate result because of what we're going to see here in a second. Now, when we average our initial and final velocity, what are we going to be averaging? We're going to be averaging a plus 9.2 meters per second and a minus 9.5 meter per second. Okay? That's going to give us a pretty small average velocity. So we do (9.2 meters per second minus 9.5 meters per second over 2. Now, we're not subtracting the velocities, we're adding. So maybe it would be better to write this as plus the quantity negative 9.5 meters per second. In any case, we're going to get an average velocity that's negative 0.15 meters per second. So that our time interval, being our displacement over average velocity, is going to be what? It's going to be approximately our displacement, which is negative 0.33 meters, divided by our average velocity, which is about negative 0.0, no, it's not 0.015, it's 0.15. Fix that off camera. And the rest of the calculation is simple, so I've completed it. So it's our negative 0.33 meters divided by our negative 0.15 meters per second, approximately 2.2 seconds. Now, actually, I think that is a little high because I said that the velocity changed by somewhere between 0.2 and 0.3 meters per second. I went with the high change, which gave us a high result for our negative average velocity. Okay, it would actually be, no, actually be a little less than that. Well, I'm puzzling over it. Work it out accurately. 2.2 seconds isn't bad, and the reason I hesitate here is simply that accelerating at 9.8 meters per second downward every second, or changing velocity by negative 9.8 meters per second every second, which is what this says, we're going to change by the negative 9.2 meters per second required to bring us to rest in less than 1 second. So we're going to be up less than 1 second, and we're going to come back down to the 2.03 meter position in an equal time. And we're going to be moving pretty fast. So our actual time, I think, is going to end up being a little less than 2 seconds, just looking at it intuitively. If you understand what I said there, you'll see it. But one way or another, be sure you calculate this sort of thing pretty accurately, although I wouldn't strongly penalize incorrect rounding, especially for the 121 class. This calculation is pretty critical on getting this result accurate.